Hey guys, today we're going to be talking about graphs of polynomials and all about what the graphs kind of look like and important information that you need to know and to find in order to be able to sketch a graph of a polynomial. So, first thing we need to talk about is the degree of a polynomial. So, the degree can be found two different ways depending on what form of polynomial you are given. If you are given a polynomial in standard form, as the first equation is shown, your degree is going to be the highest exponent. So in this case, this polynomial has a degree of 4. If we are given a polynomial in factored form or graphing form, like the equation on the right is shown, we count the number of x's that we are given to figure out the degree. So we do have 1x here, but because it's being squared, this really counts as 2 x's, because if we square an x, we get x times x, which is x squared. And then we have this third x. So this guy would be a degree 3 polynomial, or we know that as a cubic as well. And the reason why we count the x's when it's in factored form is if we were to actually multiply this all out, we would effectively have x times x from this x squared, which gives us x squared, times another x, which gives us that x cubed. And that's, if we put it into standard form, that x cubed would be our highest exponent. So that is the two different ways to tell degrees depending on what form of the equation we have. Now, the degree is going to determine what our function is going to look like. And there's a big difference between even degrees and odd degrees. And that deals with end behavior, which we'll talk a little bit about later. So with even degree polynomials, we get things like parabolas. Or if we see a 4th degree polynomial, we'll see some different shapes come about. But one thing that we can see with the even degree polynomials is that the end behaviors are going to end up the same direction. With odd degree polynomials, so this could be like a linear equation, a cubic equation, something to the 5th degree. Linear would be our straight line. We also have our cubic. We could have a 5th degree polynomial like that. And if you notice, all of the end behaviors to our odd degree polynomials are going in opposite directions. So something to help you remember this is odd degree will go in opposite directions, and even degrees will go in the same direction for end behavior. So the end behavior is not only based off of the degree, but it is also dependent on if the function is positive or negative. So if we have a positive even degree polynomial, like a basic quadratic, which has a parabolic shape, our end behaviors are going to be up and up. It's even, so we know the end direction is going to be the exact same. And it's positive, so we know we need to end on the right side in the positive direction. Now, if we have a negative polynomial with an even degree, that negative is going to reflect our polynomial over the x-axis, creating both of our end behaviors to go down. So down and down. Now with odd, odd is opposite. So if we have a positive odd, we know we want to be ending in the positive direction, which means we will be starting in the negative direction. So we'll be starting from the bottom left, going up to the top right. Now the same thing, if we took that polynomial and we made it negative, we're effectively flipping the polynomial over the x-axis, which would flip our end behaviors around. So we would be starting on the positive left side if we're looking at the y-axis and ending downwards. So we can always tell if a polynomial from the graph is positive or negative by looking at what direction our graph is ending, going off to the right side. So if we look at the graph left to right, if it's positive, it will always go up to the right. If it's negative, it will always go down to the right side. Whoopsies. So that is kind of degree and end behavior. That just determines roughly what our polynomial is going to look like, as well as how our polynomial is going to end. So the next important information to determine for graphing is if our graph has any multiplicities, and we need to figure out what the zeros are, or the X-intercepts. The best form for graphing is having your polynomial in factored form. So if you do not have your polynomial in factored form, I would recommend using polynomial division, which you can find a video on that in our YouTube channel, to get the polynomial in fully factored form. So, multiplicities. This is how your graph is going to look as it crosses through your x-intercept values. And how to find the multiplicities, you have to be in factored form, and these are the powers of your zeros, of your x-intercept points. So the first step in graphing, once we have it in factored form, is to determine the x-intercepts. So we can find the x-intercepts, or the zeros of this function, by setting our equation equal to 0 and using the zero product property. From this, I know that I will have one x-intercept at -3, 0. I will have another one at -1, 0, and another one at +4, 0. If you need help with finding the x-intercepts or using the zero product property, refer back to our solving quadratics video. So with these x-intercepts, it would be really nice if our function just passed through them like normal and fluidly. However, because we have some exponents on a few of our zeros, our graph is going to look a little bit different at those places. So at our -3 x-intercept, this term had a square, so we call this a multiplicity of 2. Our x plus 1 term did not have any exponents on it, so we can say it either doesn't have a multiplicity or it just has a multiplicity of 1. And then finally our last term, our x minus 4, is raised to the third power, so this guy has a multiplicity of 3. Now the cool thing is at these x-intercept points with these multiplicities, it actually looks similar to the graph if we were just to graph x plus 3 squared, or just x plus 1, or just x minus 4 cubed. So they'll look like a parabola or a cubic function as it passes through those x-intercept points. So first things first, let's go ahead and plot the x-intercept points, because those are some easy values that we do know. So we have one x-intercept point at -3, one at -1, and then our final one at +4. All right. Now that we know our x-intercepts, we know the multiplicities, so we'll kind of have an idea of what that's going to look like. We do need to determine the end behavior so that we can figure out where to start and where to end the function. So in order to determine end behavior, I have to determine the degree of the function. So since it's in factored form, I'm going to count up my x's. From the first term, I have 2 x's since it's being squared, and then another one from my second term, so that's a total of 3 x's so far. And then I have 3 more x's from my last term, so this polynomial has a degree of 6. An even degree means that it's going to start and end the same direction. And because my polynomial is positive, I know that my graph is going to start up and end up. From there, I can figure out how to go through my points. So at -3, I have a multiplicity of 2. This is going to tell me that my function is going to bounce off of that point. Note, if a multiplicity is even, your function will bounce off of the x-intercept. All right, so I will take my function down to the x-intercept and I'm going to bounce off of it since I have that multiplicity of 2. If you guys notice, this kind of looks like a parabola, which quadratic functions create parabolas. So we can kind of think of this x plus 3 squared term as its own mini little parabola within our function, which is why it kind of has that bounce off of the x-intercept. Our next point that will be passing through is -1. It has a multiplicity of 1. Since it has an odd multiplicity, it's just going to cross through. And because it has a multiplicity of 1, there's not going to be anything super special happening at that point, so we are just going to cross through. If you think of this as zooming in to that local x-intercept value, it looks like a straight line crossing through, which is good since we have a multiplicity of 1. So now our function is going to turn around to pass through the very last x-intercept at when x equals 4. This guy has a multiplicity of 3. This means that as our function is passing through this x-intercept, it is going to take on a cubic shape since our multiplicity is 3. So when we continue on graphing our function, we are going to graph it as a cubic passing through that point. And that was a little messy, so I can clean this up just a little more. So if we zoom into this x-intercept, that guy looks like your your cubic function that is passing through. And that is what multiplicities will do to your function. It will just change the shape of the function and how it is passing through those x-intercept values.